Hi guys, today's notes are on 4.8 graphs of polynomial functions. We will finish these notes in class, not this page, but like the section. So let's first talk about what we've learned so far this chapter. So in this chapter, we've learned that zeros, factors, solutions, and x-intercepts are very closely related concepts. Here's a summary of those relationships. So a zero. K is a zero of the polynomial function f. Let's say you're given that. If k is a zero, then x minus k is called a factor, right? So the signs switch of the same polynomial. K is a solution of the polynomial equation, or we call it a root, if we have f of x equal to 0, right? We have to have it set equal to 0. If k is a real number, then k is an x-intercept of the graph of the polynomial function f, and the graph of f passes through k comma 0, which is a point on a graph. And so let's now talk about the location principle. The location principle states that if f is a polynomial function and a and b are two real numbers, and when you plug in a to the function f, you get a y value less than 0, and when you plug in b, you get a y value greater than 0, then f has at least one real 0 between x equals a and x equals b. Okay, so let's take a look at what this means. So what this is saying is that if you have a graph, and let's say we have a here and b here, let's say when I plug in a, I have a negative y value down here, and when I plug in b, I have a positive y value up here. No matter what, in order to connect the line from a to b, right, like it could go down or up, whatever it is, like there's going to be a real solution here, which is our x-intercept. You can't say there's no solutions between a and b. And to use this principle to locate real zeros of a polynomial function, you can find a where the polynomial function is negative, and another value b where the polynomial function is positive. And then you can conclude that the function has, negative and positive, you can conclude that the function has at least, one x-intercept between a and b. Sorry, I just wrote that a lot smaller. Feel free to use that space. So let's take a look at what this looks like. So we're going to actually use some graphing technology. Let me zoom out here and grab my graphing calculator. Please take a moment and pause your video and do that. So we're going to find all zeros of this function, which is a cubic function, and it's not factorable. So we know that we technically need to do p over q. Is that correct? Right? So what we're going to do is let's list out all the possibilities. Plus or minus 1, 2, 3, and 6. It's actually 6 over 6. So this one is your p, and q is your leading coefficient. But it's going to be the same. Okay. I'm going to list out all my options here because I have this mismatch of things, it doesn't mean I actually have a list of our possibilities. Plus or minus 1, 2, 3, 6. All of those are over 1. So then I'm going to do 1, 2, 3, 6 over 2. But I know that divisible by 2, those numbers have already shown up here, right? So I'm going to have just plus or minus 1 over 2, plus or minus 2 over 2. See that right there? So I'll do 3 over 2. 6 over 2 is divisible, and it's right here. So then I'm going to go 1 over 3, 2 over 3, 3 and 6 can both be divided by 6, so by 3, so I know that I've already listed those out here. And so the last option is plus or minus 1 over 6. Okay, 2, 3, and 6 can all be reduced, so those options have already shown up here. So let's take a look and see if we can now use the graphing calculator to make a table and eliminate some of these options. So please follow along with me. You're going to go to y equals, and we're going to type this in. So 6, let's do it over here, yeah. Okay, 6x to the third power, so here's your caret, plus 5x squared minus 17. Make sure you use minus instead of negative because it's in the middle. X minus 6. Okay. So we're going to use this graphing calculator to make a table. So you're going to go to y equals, put that in, right, and table. So you go second graph up here to find the table values. Okay. And we know that we can look for our zeros. So this one actually is an x-intercept. So take a look, and we know x equals negative 2 is a solution. Okay, so we know x equals negative 2. Let's pretend like we don't know that, though, because if I knew negative 2, I could do a synthetic division and then do quadratic formula or factor, right? And that would just save us so much time. But what if we had a more complex problem? Okay, so just bear with me and pretend like if you see a more complicated problem, this is what you would do. So let's pretend like they're all fraction solutions. So now we're going back and looking for some more zeros, but you see how it keeps getting negative, more negative. And we see how here it goes up, 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 and then it comes down. So between negative 1 and 0, it goes from positive 10 to negative 6. Yeah, negative 6. So that must mean between x equals negative 1 to 0, there is an x-intercept in that space. Okay, so then it goes negative. And then from negative to positive, between 1 and 2, there's another sign change, plus to negative to positive. So that's from 1 to 2. Okay. So let's take a look now at our rational roots theorem, because, oh sorry, could you even see that? I apologize. You guys see how like there's a 0 at negative 2, but positive to negative sign change from negative 1 to 0, and a negative to positive sign change from 1 to 2. Okay, so now we're going to use the location principle to assume that there's a 0 here and a 0 here to narrow down your choices. Now, in the rational roots theorem, unfortunately, from negative 1 to 0, there are no, that's not the numbers, right? But there are a lot of numbers from negative 1 to 0, a lot of fractions. This is negative 0.5, this is negative 0.667, right? And negative 0.33 and negative 67. And this one also works. So take a look and notice that we have 1, 2, 3, 4 negative fractions that could fall in this range. However, from 1 to 2, there is only one possible x equals 3/2, which is 1.5, right? And so between 1 to 2, there's only one solution, which means we think this should be it, assuming that it's not an irrational solution. So let's do a quick check. So we're going to use synthetic division to confirm that this point is a 0. And so let me write this in. X equals 3/2. I'm not going to use decimals just because fractions are the most accurate number. So 6, 5, negative 17, and negative 6. So instead of pulling out your calculator, can I walk you through what I would do without a calculator at this point? So I would drop the 6, and I know that I'm going to multiply by 3 and divide by 2. Now dividing always gives you the smaller number first, so I do divide by 2 first. So I'm going to say 6 divided by 2 is 3, times 3 is 9. 9 plus 5 is 14. 14 times 3 halves is 14 divided by 2, 7 times 3, 21. 21 minus 17 is 4. 4 divided by 2 is 2, times 3 is 6, and here we go, no remainder. So x equals 3 halves is a solution. Okay, we also know from before that it's x equals -2, but let's assume we don't know that. Okay, so let's take this now. We started with a cubic. We're dropping it to an exponent of 2. And now we have x minus 3 halves. But we don't write fractions in factored form, or factors with fractions in it. So we want to multiply both of these by 2. Okay. So then I have 2x minus 3 to get integer coefficients. Now, if I multiply this piece of my equation or function by 2, I have to balance it out by making another part smaller. So I'm going to divide all of these by 2. So that gives me 3x squared plus 7x plus 2. And how you can check that your function is factored correctly is that you could now multiply 2x times 3x and we get 6x cubed. And so I know my leading coefficient is correct, I know my y-intercept is correct, and now I can keep going. So the idea now is, I do know that this one is x equals 3 over 2. It says to find all real zeros. So we're going to find the last one. And we know it's one of these numbers, these fractions right here that I've underlined, but it's going to be a negative. Now, let's factor. We need numbers that multiply to 6 and add to 7. So I know that's going to be 6 and 1. Okay, so let's see. I know this is 3x times x. And so this will be 3x and x. And since I know it needs to multiply to 6, that means it has to be 3 times 2. And then plus 1. Because these two right here, when I distribute, 3x times 2 is 6x plus 1x will give me 7x. Okay. Over here I'll have 2x minus 3. And so this one is x equals 3 halves. This one, or this factor, gives us a solution of x equals -1/3. And this one gives us x equals -2. Okay. Now we can check using our graphing calculator by making our calculator do some work. And this is a really cool function where like maybe we can't find the fraction here, but if you go to table set, you see above window, so I'm going to go second table set, you can actually change this. Independent is x, dependent is y. So I can say instead of auto-populating or auto-filling our x's, I'm going to say ask. Okay. Now I can go back to my table, and it's all blank, but it's not really blank, it's just waiting for you to put in your x values. So let's start with our whole number. I'm going to put -2. If you put minus, that negative is at the beginning, so it has to be a -2. Once you hit enter, you get 0, and it confirms. So now let's do 3 over 2. 3 divided by 2. Changes it to a decimal, but we know it's an exact value. Look at that other 0. And then I have -1 divided by 3. And that's also 0. Now, the only thing you want to be careful of is if you mess with your table like this, you want to go back to table set and change it to auto so that next time you look for your table, you don't wonder where your table of values went, right? So just make sure that's back. Okay, now let's move on to the math. Oh, I should talk about, is this something you'll be asked to do on the test? You won't be asked or given something like this where you have to use your graphing calculator in our class, but later in calculus or pre-calculus, you might need to use the location principle and the rational roots theorem, and being able to use your graphing calculator will just simplify and make things a lot faster in the future, okay? So let's talk turning points. Once again, something that's really important for calculus. Another important characteristic of graphs of polynomial functions is they have turning points corresponding to local maximum and minimum values. Okay. The y value of a turning point. Now, turning point is when you change from a positive to a negative slope. is called a local maximum if that point is higher than all the other points in the area. Now, we don't call this a total maximum or just a maximum because the maximum of this cubic function is technically increasing forever. So it is infinite. But in this area, right, there is a local maximum because that point right there is higher than all the ones around it. And if it's the point is lower than all the nearby points or the y value, then it is a local minimum. Okay. Turning points on a graph help determine the intervals for which a function is increasing or decreasing. To find or estimate your turning points, you have two methods. You can make a table by plugging in values, which is a pain in the butt, or your graphing calculator. But the most efficient way is using graphing technology or graphing software, which is when you use your graphing calculator or Desmos. Okay, so let's use our graphing calculator to do this. Now, here I've typed out the steps in case you struggle to remember how to find max and min. So I would highlight this box perhaps with a highlighter just so that you remember to look back here if you forget what the steps are. So let's do our last two examples, and this will be embedded in here. Our x-intercepts are, let's see, -1, -2, and 1, right? All of our signs change. To find your y-intercept, you plug in x equals 0. And we know that since all of our x's are 0, it's really just your leading coefficient times each of your zeros, or x-intercepts, right? So it's 4 times, sorry, not your zeros, your k values, or the opposite of them. So 4 times 1 times 2 times -1. Right, because all of your x's are zeros. So that gives us a -8 y-intercept. I can write these as points or ordered pairs if I want to. I think I'm okay as is. Now, local minimum or local maximum, there could be more than one. So let's take a look. We're going to graph this again. For parentheses, x plus 1, x plus 2, x minus 1. It's a cubic function. Uh-oh, my window is off. So in order to fix that, we are going to go to zoom standard, which is 6. Okay. So I have one local maximum, one local minimum. Let's put in our x-intercepts at -1, -2, and +1. There's a y-intercept at -8. And we know that according to our leading coefficient, which is positive, our graph is going to continue to go up. Okay. There are 3 solutions. The degree is 3. So in this case, we know there's no imaginary solution. So that's why I didn't have to worry about like ups and downs above the graph. So we know we're going to have to come down for this y-intercept, but do I know if my y-intercept is a local minimum, is the minimum to the right or to the left? And we don't know that, but according to the graph, we can sort of tell that we're close, but we're not exact. So let's go to table and see. And it looks good, but how can we be sure, right? So what we're going to do is we're going to go back to table and we're going to make the graphing calculator do some work for us. You're going to hit calc, which is up here, so it's second trace, and then go back to, we want to find a minimum point first, okay, local minimum. Now, do you guys remember we need to be on the left side and the right side? Because if you do the whole graph, then it will just pick whatever the lowest point is of the entire graph, which is infinity, right? So we need to be on the left side of our minimum, and then we will move to the right side of our minimum. And so now in between these 2 points, it will give me the local minimum, which is at x equals 0.215. So this will be at 0.215. Okay. The y value is negative 8.450. And so that means I'm going to have a local minimum down here. Okay. Notice like my minimum is a little lower. My local maximum, I'm going to do the same thing, and I'm going to go second calc and go down to 4 for maximum. So now I'm on the right side, but I need to be on the left. So I'm going to go over here. And you can be anywhere on the left, like a little bit on the left or a lot on the left, whatever works for you. I like to just go a little more. Okay, and hit enter again, make it guess. And so now our maximum is negative 1.549. I'm just rounding to 3 because it seemed like a good place to start. I will tell you on a test what you're rounding to. Okay, so this is our point. And so I want to go from negative 1.5 to 2.5, which is like right there. Okay. Now the last thing you would be asked is what interval, over what interval is this function increase? So do you see how like if you broke your function into 3 pieces using your x values of your min and max, right? So this is negative 1.549 and this is 0.215, those x values. Now I'm looking at like from the left side of this, all of my slope is increase. Okay, so on the left side of this x value. So I can say from negative infinity to negative 1.549. Now 1.549 is not included because that's at the very top, so it's no longer increasing. That's where the slope is 0. So I'm going to use parentheses to show that it doesn't include that number, and infinity is never included because it's not an actual number. And then if you go down here, there's another piece that's increasing. So then I'm going from 0.215 all the way to positive infinity. Okay, non-inclusive. There's only one section of this graph in the middle that's negative or has a negative slope, which is when it is decreasing. And so we're going from negative 1.549 to 0.215. And so these look like points, but they're not points. They are sections on a graph. Okay. So why don't you take a moment, pause the video, try example 2, and then once you unpause, I will have the answers for you to check. Okay, so take a look real quick at this. We know our x-intercepts are the opposite signs. Okay, there is a repeated solution here at x equals 1, which you can see on your graph as like a parabola. It's upside down. We found our y-intercept by plugging 0, which is negative 4. And then local minimum and maximum, you had to be really careful when you were putting the left and right bounds of this local minimum, because if you went too far to the left, then whatever point you put down here as your left bound is lower than that one. So your calculator would have given you this point. So just make sure you're very, very carefully zoomed in, and you want your cursor like right here per se. Okay. And then anything on the right. So here are your local minimums. Your local max is that point, which is 1, 0, which you don't need a calculator for that. And so our intervals, which are increasing, are right here and here. And then decreasing is from negative infinity to that first x value that we found, and from 1 to 1.693. Okay. Let me know if you have any questions in class when you see me next.